In our lives, we measure a whole lot of things. We measure things like our weight and our height. So I may say my weight is 180 pounds. Well, those physical quantities, we almost always use an amount. So for example, 180, 180, and a unit, pounds. So we have those two things together, 180 pounds. And we call that a magnitude. And the magnitude is just the amount and unit of how much. So we use this all the time. I'm 6 feet 4 inches tall. I'm not going to write both of them. Pretend I'm just 6 feet. 6 feet and an amount and a unit. So the magnitude of my height is 6 feet. These things, though, are kind of limited because in physics, we really like to make predictions about how these will result in the future. So for example, if I push on an object, I want to know how it's going to move. If I'm going in a certain direction at a certain time with a certain speed, I know where I'm going to end up 30 seconds later. So we make those predictions. But to make those predictions, something like the grocery store is 4 miles away, and I'm walking 3 miles per hour. It doesn't help me. It doesn't tell me if I'm walking towards the store. So in physics, we use these things called vectors. Vectors are the counterpart to these directionless things. These have directions. So they have not only a magnitude, but also a direction. So a magnitude might be 4 miles. A direction might be north. So we always have these. When we need any variable that has to do with direction, where direction is important, we're going to use vectors. So examples, force is a vector, right? If I push to the right, it's going to have a different effect on an object than if I push to the left. Temperature is not a vector. The counterpart is scalar, has only magnitude, no direction. Okay, so when I said the thing is 4 miles away, that's a scalar. It doesn't have a direction associated with it. As soon as I have a direction associated with it, it's a vector. Okay, temperature doesn't have a direction. We don't say 3 degrees southeast. We don't really talk about that. Time doesn't have a direction, up, down, south. Velocity, we're going to use this quite a bit. That is a vector. Weight, it turns out, is a force. So that's a vector. It has a direction of down towards the center of the earth. Mass is how much material. That's not a vector. Acceleration has a direction. So that's a vector. Displacement, which we're going to talk about very soon, also is a vector. Distance, we say, I ran 3 miles today, but it doesn't have to be in a straight line. Displacement is in a straight line. Charge, electric charge, no. Momentum, yes, we'll learn about all that stuff in the future. Energy, no. All the things I crossed out, those are scalars. You don't need a direction. These other ones, we always want to have a direction associated with them. Okay, so how do we represent them? What do you think? An arrow. An arrow is a good way. We could specify it. We could say, like I said, 4 miles north, or 4 miles up, or 4 miles down, whatever the direction happens to be. A satellite is 4 miles over our head. I don't know. A plane, I guess, would be better than a satellite. But better is to write an arrow, and sometimes they'll 4 miles in that direction. Well, I'm going to start using meters because I don't use miles very much. 4 meters, that's almost 4, that's a little more than 4 yards in that direction. So when we're talking about things, this could be a displacement of 4 meters. You can represent a velocity that way. I'm going 20 meters per second in that direction. I could have a different one over here. Okay, that's a vector. Maybe it's a force, 5 newtons. And it becomes really clear how we use these once we get into solving problems. I just want to show how we represent these vectors. Okay, very frequently in a lot of places you'll have either bold, or like, so if I say this A is vector A, sometimes I'm going to write it like this with a little arrow over the top. Sometimes in text you'll see it as bold. Much more frequently, I'm just going to forget to write the vector notation in my class, but it's good practice. The last thing I want to talk about is how to add these things together, because we need to process these. We need to make predictions and we need to make calculations. Okay, so let's say, and let's just talk about displacement. 5 meters. I walked 5 meters in that direction. And I walked another 10 meters in the same direction. Okay? To add these things together, we just put them in a line. We line them up like this. And it looks kind of silly to say this, but the way we construct this is what we call tip to tail. And what you do is put the tip, there's a tip of one, attach it to the tail of another one. And you'll notice I can't change the directions of these things. I can move them around. You saw me move it around, right? I can move this anywhere I want. I could put it over here, make a tip to tail that way. I could put tip to tail that way. But I have to maintain the same magnitude, the same size. And you'll notice I drew this twice as big as the other one. And I have to maintain the same direction that I had before. Okay, so if we do that tip to tail, what we then do is we represent the sum by what we call the result. And it's hard to draw in one dimension just because it overlaps. If I really wanted to draw this carefully, I would put it right on top like that. But I'm going to offset it a little bit just so you can see it. And so 10 plus 5, 15 meters is the resultant 15 meters to the left. That's pretty easy, right? Okay. If you have two and they're in opposite directions, there's that one, and then I'll have this one going in this direction. We do the exact same thing. Don't do that. Still getting used to this tablet. We add them tip to tail. So in other words, the tip of that big one is touching the tail of the other one. They make one continual path. Then you draw the resultant from the beginning to the end. It's kind of the shortcut. So let's say this was 10. Instead of meters, let's use a velocity, meters per second to the right. Let's say it's a toy plane is going 10 meters per second to the right, and it faces a airspeed, a wind speed of 2 meters per second in the other direction. Well, 10 minus 2 is 8 meters per second is the resultant. That's how the plane would fly. So that's how you add vectors in one dimension. In the next setup, I'm going to show you how to add vectors in 2 dimensions. And then we're going to actually break down vectors and figure out how we do the numbers for adding vectors in 2 dimensions.